So this is the fourth and last lecture on the course on Hessians and the Lefschetz properties. In this lecture, we're going to talk about Hessians and their relations with Jordan types for Artinian Gorenstein algebras. It will be linked with all previous lectures. Let's recall the concept of Jordan type for an Artinian algebra in general, and use it to understand how deep an algebra fails SLP or double LP. An informal introduction: the Jordan type of a standard graded Artinian algebra, not necessarily Gorenstein, is the partition of the total dimension over the base field, which we are assuming, as in all the course, is of characteristic 0. There is a partition of the total dimension as a finite-dimensional vector space given by the blocks, the Jordan blocks, the size of the Jordan blocks of the multiplication map for a generic linear form of degree 1. It's easy to see that this multiplication map is nilpotent, because if we take the power of the map with exponent greater than the focal degree of the algebra, since mu L to E is equal mul LE, and this is 0 because every element we are assuming that this exponent is greater than the focal degree of the algebra. Or in the Artinian case, the last non-zero graded part. A priori, these Jordan blocks, the size of these Jordan blocks depend on the linear form L, but there is an open Zarisk subset of A1 where it is constant. So take a generic L. This is the Jordan type of the algebra. Sorry? To be more precise and a little bit more general, let A be a standard graded Artinian K algebra, and let M be a graded A module, and L a linear form in the algebra. Consider the multiplication map in the module given by Lx. Since L to D plus 1 is 0, and we have this condition, we conclude that mu L is a nilpotent K-linear map. Therefore, the eigenvalues are 0. So the canonical Jordan formula for this nilpotent map is a matrix it's the matrix mu L it's 0 here, and inside we got these Jordan blocks of size ni, which 0 in the diagonal, one here, 0 here. Again, it's a partition of the total, sorry, I call the matrix with the same letter of the module. Matrix of mu L with respect to some Jordan basis. It's a partition of the total dimension of the model as a k-vector space. And this partition is called the Jordan type of the model with respect to L. In 1, in S. Sometimes we will write it in this way. It's possible to choose a non-increasing or non-decreasing order. It's not relevant. So there is a direct sum decomposition as scar linear spaces, vector spaces of M into Mj, which are ML cyclic invariant subspaces. We call a mu-L invariant basis of one of these cyclic subspaces Mi, a string of length Ki, which is the dimension of Mi, which here I'm calling Ni. Sorry about the different notation. Let me do a very easy example just to start to understand this easy concept. Let me start with a very easy example that actually we studied in the previous lectures. A of x yz over x squared y squared z squared, whose Hilbert function is 1, 3, 3, 1. And we have these standard k-linear basis of each graded part. And let me choose x plus y plus z as the linear element in A1. By abuse of notation, I use the same capital letters to the image of the indeterminates in the quotient. So let me start with the first. So I'm going to consider A as an A module over itself. So we are interested in the decomposition of A in mu L, cyclic mu L invariant subspaces. Let me start with the cycle C1, which starts with V1 equals 1. 1 L, doing the computation of L square, the x2, y2, z2 is 0. So it's 2 times xy plus xz plus yz. Add 3. It's 3 times xyz. It ends the first string. So n1 or k1 equals 1, 2, 3, 4. Let me compute C2, which is a string not starting in L. There is nothing in degree 0. It's over in degree 0. But in degree 1, we still have a 2-dimensional space. Let me choose V2 equals x, L, x, L squared, xl, x squared is 0, so it's xy plus xz. And this guy is 2xyz. So n2 equals 3. And we still have a possible one, two, three, 4, but this guy is here. So taking modulo this one, I finish here, 2. And in the same way, sorry, in the same way with V3 y, yl, and 3 equals 2. We are trying to get in the composition as a direct sum. So I use this string. Let me put this information in a diagram. I'm going to write the Hilbert function in the diagram. 1, 3, 3, 1, 1, 1, 2, 3, 1, 2, 3, 1. And here, I'm going to write down the strings. The first string has length 4. This way. And the other two strings they have length 2. So this diagram is telling us that the Jordan type of A with respect to L is 4 plus 2 plus 2. Sometimes I'm going to write in this way. And in fact, in the monomial case, it's always the case that this linear form is general enough in order to the generic Jordan type of A is precisely this one. The monomial case, L, the sum of the variables, is general enough to compute the generic Jordan type of the algebra itself, which I call the Jordan type of A. Given a partition, the so-called, this is the partition P, the so-called dual partition is the partition obtained from P, exchange rows and columns in a Ferrer diagram. It is a Ferrer diagram. And exchange rows and column, the diagram becomes so the dual partition given by Ferrer diagram in this case actually encodes the Jordan type It's the Ferrer diagram of the Hilbert function. And in this case, for 2, 2 is actually the Jordan type of A. It's not a coincidence, as we'll see in the sequel. It's always the case when A has the SLP. There is a natural partial order is the dictionary order among two partitions. of n. And if we have repeated terms like here, I write down with a symbolic exponent. Again, if the field is of zero characteristic, there is an open Zarisk subset of A1 where the Jordan type is constant, and this is the Jordan type of the model, or in our case of interest is the Jordan type of the algebra itself, which is the same to say that is the Jordan type of A with respect to a generic L. Suppose that A is a standard graded Artinian K algebra, then A has the double P if and only if the number of parts of the Jordan type of A is equal to the maximum value of its Hilbert vector. I'm not prove these result in details, but the idea is that the number of parts of the Jordan type is always greater than or equal to the Spanner number of A. And we will see when I introduce an algorithm to compute the Jordan type using these diagrams, we will see why it's always the case. And in the case L is a double P element, so we are assuming that A has the double P. In this case, actually, this number coincides the number of parts of the partition and the maximum value of the Hilbert function. So the previous result says that we can control or we can detect double P using with the Jordan type of A. Moreover, we can also detect the SLP. Again, I will not prove the theorem, but as soon as I introduce an algorithm to compute the Jordan type in a Ferrer diagram of the Hilbert vector, it will be more or less trivial to see why it's true. It's just an interpretation of the, it can be seen as an interpretation of the algorithm. From now on, we are going to go in the direction of to give an algorithm to compute the Jordan types for an AG algebra. We take the multiples of L in degree I, so they come by the multiplication of I minus 1 by L, and we have this quotient as a co-kernel. Then I'm gonna choose a base of LAI and took a complementary base and identify the co-kernel with subspace of AI up to a choice of complementary bases. So we will define Aij, the space of V in AI hat such that V multiplied by L raised to the power of J is 0, but to the power J minus 1 is non-zero. So they are a string Aij a string starting in AI of length J, all the strings of this type. So Aij is the number of strings starting AI of length G. Ag is the number of strings of length J. There is only one string of length D plus 1, which this string is starting in 1, A D plus 1 equals 1, and the string A0 D plus 1 is 1, L squared, L to the V. For a generic L, it's non-zero, so this is the only string, which is a string in the bottom of the Ferrer diagram of the Hilbert vector of A. more or less by definition and by interpretation of these numbers, the Jordan type of A is J EJ. Sorry, my notation is not consistent. EJ. Oh, okay, it's consistent. It's not consistent here. EJ is the number of strings of length J. So this is the Jordan type of A. So here is the beginning of an algorithm. Now, how to compute these numbers? And just by definition, and basically in our algebra, you will see that using the rank Rij L to the J from AI to AI plus J Rij is the rank of this multiplication map, which we saw in the last lecture. That is the rank of the Hessian E plus J dual I of F, but it's the same as the rank of Hess D minus I minus J I of F. So the conclusion of the lemma is that the Jordan types depends only on the ranks of certain mixed Hessians. So the algorithm is based on the computation of ranks of certain mixed Hessians. This is the conclusion. The Jordan type of a standard graded Artinian Gorenstein algebra depends only on the rank of mixed Hessians. More precisely and explicitly, we got this huge formula, which I'll not compute in general. Instead of, I'm gonna show you the algorithm working in particular cases. The corollary is that the Jordan type of A can be obtained algorithmically from the Ferrer diagram of the Hilbert vector of A by computing the rank of certain mixed Hessians. This is my viewpoint. Let me write this here. The Jordan type of A can be obtained algorithm from the Ferrer diagram of Hilb A by computing the rank of mixed Hessians. Of course, in the special case, if A has SLP, the mixed Hessians that matters actually are the higher Hessians that controls the rank of the map in complementary degree. So if we have a Ferrer diagram of an SLP, Ferrer diagram of Hilb A, and we are assuming that A has SLP, since all the higher order Hessians have maximal rank by the SLP, we got these maximal strings. In particular, it is easy to see that the Jordan type of A is precisely the partition given by the dual partition of the Hilbert factor. Here is the biggest part, and so on, so on, so on. But if A does not have SLP, we get smaller strings. So in general, the Jordan type of A is a partition which is less than or equal the dual of the partition given by the Hilbert vector. And it proves, it's an idea of the proof of this general result here. Of course, in general, if Hilb A is unimodal, then we got this. And SLP is equivalent to this picture, which is saying that the Jordan type is the dual of the Hilb. Now, till the end of this lecture, I'll be interested in compute here, Jordan types using the algorithm, Jordan types of algebras, Artinian Gorenstein algebras, with low Sokal degree. The way I'm going to compute the necessary Hessians is using geometric information of hypersurface with vanishing Hessian with low degree. But when we are talking about a hypersurface of degree D, the defining equation is considered a reduced polynomial in order to get a bijection. But in Macaulay-Matlo's duality, the form F that gives rise Artinian Gorenstein algebra of so-called degree D is not necessarily reduced. Moreover, the classification of forms with vanishing Hessian was done in low dimension and low degree only for irreducible hypersurfaces. So we have to understand how use Macaulay-Matlo's duality and use the geometry to get the Jordan type. We want to restrict ourselves to the irreducible case. How to do this reduction to the irreducible case? Let me say something about what's known the first result that I will use is the theorem of Dinka-Papadima, which says that theorem Dinka-Papadima that F in RD any polynomial and little f is radical homogeneous of degree D, homogeneous of degree D prime, then the topological degree of the polar map of F and the polar map of F are the same. In fact, it depends only on the topology of the complement of Pn minus x. In particular, as f is 0, if and only if as f is 0. And another result of CIMPA that we use, CIMPA, let x L1 LD be an arrangement of hyperplanes then has x is 0 if and only if x accord. Now, how to use it? Together with Macaulay-Matlo's duality to study Jordan types of all algebras, let me say, of degree d equals 3 and codimension n. From Macaulay-Matlo's duality, A is of this form. If we are interested in study the Jordan type, we have to understand the rank of this Hessian. So we are interested in the only Hessian that matters, which is the first Hessian. But the first Hessian of f is 0 if and only if the first Hessian of its radical is 0. But if f is not reduced, its radical has degree less than 3, and so it's trivial. There is nothing to do. So we can assume that f is reduced. CIMPA reduce to the case f is L1, L2, L3, or f is irreducible, but in this case, it's an arrangement of hyperplane, and the Hessian is vanishing if and only if it's a cone. Again, there is nothing to do. We are dropping the codimension, so we can reduce ourselves to the case f is irreducible. And let me start the discussion about the Jordan types in so-called degree 3. Jordan types for Artinian Gorenstein algebras could dimension n, so-called degree 3. The Hilbert vector of A is 1 and n1. And let me introduce the only invariant that matters, which is the rank of Hess of F, which in the notation of the algorithm, it's called R11. Is the rank R11 is the rank of the multiplication map from A1 to A1 plus 1. It's the rank of the Hessian. Using the formula given in theorem 4, we get these numbers, which give us these Jordan type. 4 once, 2 R minus 1, 1 2 times n minus r. Let me explain why, without using the theorem, either the formula. This is the longest string, which starts with 1, and it's 1 L squared L to the third power. The number of strings of length 2 is starting in A1 is precisely R11, which is the rank, the possible. These are the possible. But this one was used in the biggest string. So here we have R potential strings of length 2, which is the rank of the first Hessian. But in fact, we have only r minus 1 of length 4, r minus 1 of length 2, and all the others must have length 1. How much? I recall that here we have n, which the Sperner number is the biggest Hilbert vector, value of the Hilbert vector. So here we have n, r. So here, n minus r. N minus r twice is the number of ones in the Jordan type of A. And this is the string diagram for a Artinian Gorenstein algebra of codimension n and circle degree 3. But the real question is, are all of those diagrams actually real Jordan types for a given n, for a given codimension? Of course, the answer is no, because we recall that by Gordon-Nutter theorem, if the number of variables is up to 4, yes, we are in P3. We know that F is non-vanishing, since we are not working with cones. We are actually using all the n variables. So for n less than or equal 4, the only possible Jordan type is without these parts. So it's 4, 1 plus 2 n minus 1. Because R, the rank of the Hessian, is full, is n minus 1, and here is 0. There is no kernel for the first Hessian. For n equals 5, we have Perazzo form is up to projective transformation, the only form with vanishing Hessian in 5 variables. What to say about the Jordan type of Perazzo algebra this is the Hilbert function 1, 5, 5, 1. It's the Ferrer diagram of the Hilbert function. And we got this long string. And since the rank of the Hessian, we can actually compute the rank of the Hessian. The rank of the Hessian matrix of F is 4. And this 4 is 5 minus 1. And this one is the number of independent algebraic relations among the derivatives. One relation, this is actually this one relation is the codimension of Z, the polar image. So we have here is the rank of the Hessian. We have 3 strings of length 3, and the remaining strings must have length 1. So the Jordan type of A is, sorry? Yes, okay. 4, 1 plus 2, 3 plus 1, 2. Of course, when NE equals 5, or we got the generic Jordan type, which is the one with non-vanishing Hessian, which is 4, 1 plus 2, 4, or we must have vanishing Hessian, and this is the only possibility with vanishing Hessian. For n equals 6 and 7, Perazzo proved, and we revisit the result, that if a cube in 6 or 7 variables has vanishing Hessian, necessarily it has a canonical form, and in this case, the codimension of the polar image is necessarily 1. So in this case, either the Jordan type is the generic one for 1 plus 2 n minus 1, or in this case, the has non-zero, or if it has vanishing Hessian, it must be with only one. So 4, 1 plus 2 n minus 2 plus 1, 2. This is this discussion. The classification of cubes vanishing Hessian in low dimension is part of Perazzo's classical work, revisited together with Russo. The Perazzo example is this one, which is less than the generic one. And you can compute the delta. The delta is the codimension of the polar image, or the core rank of the Hessian, which is the same. Delta is 1 in this case. Also in this case, delta is 1. But from 8, it starts to have different kinds of forms with vanishing Hessian, whose the codimension of the polar image, or equivalently, the core rank of the Hessian, grows. The first example of this kind was produced by us several years ago. And it's called the concatenation of the Perazzo algebra. Let me explain the idea of the concatenation. It's a very useful idea to produce examples with higher delta. The idea of concatenation. Let me explain in this explicit example. Let F be the Perazzo form. The concatenation of F with itself is like to produce another form which is very similar. using a new x, let me call it this one x1, x2, x3. We can share this x3 v squared and think that we are starting another Perazzo-kind polynomial with x4 uw, because v is here, plus x5 w squared. And I put a half here, half here, and sum these guys to obtain this x1 u squared, x2 uv, x3 v squared, x4, v w, x5 w squared. Now we have two relations of dependence among the partial derivatives. This product is the square of this guy, and also this product is the square of this guy. Precisely. The derivative of f with respect to x1 times x3 and the derivative of f with respect to x3 times x5 whole square. So the codimension of V is at least 2, but in fact it is 2. It's the corank, it's the delta. The number of variables is 8. 1, 8, 8, 1. Sorry. We have delta 2. 1, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1. Delta 2. This is the string diagram for A that determines the Jordan type of A, which is 4, 1, plus 2, 1, 2, 3, 4, 5, plus 1, 4. In the same way, this is the diagram I just finished. In the same way, with 9 variables, we can produce one concatenation with delta equals 3, and so on, so on. We have just proved this theorem. Let A be a standard graded Artinian Gorenstein K algebra of codimension n and so-called degree 3. Then the possible Jordan types of A are, at least in low dimension, up to 8, 9, something like that. For n less than equals 4, delta is 0. So it has the SLP, and the Jordan type is the dual of the Hilb of the partition given by the Ferrer diagram of Hilb. 6, 5, 6, 7, either A has the SLP, which to say that it has non-vanishing Hessian, or it has a vanishing Hessian and fails the SLP. And in this case, delta must be 1. And so the Jordan types is 4, 1, 2, n minus 2, and 1, 2. For n equals 8, either A has non-vanishing Hessian and has the SLP, and the Jordan type is the dual of Hilb, 4, 1, 2, 7, or A fails SLP and its Jordan type is 4, 1, 2, 6, 1, 2 if delta equals 1, or 4, 1, 2, 5, 1, 4 if delta is equal to 2, which is actually this concatenation case. For n equals 9, we have these 3 possibilities. And then it becomes to be a little bit complicated to understand all the possible Jordan types, but it is true that for any positive integer given delta, there is n and Artinian Gorenstein algebra of codimension n so-called degree 3, such that delta of A is precisely delta and it finishes the case D equals 3. Now, let me say something about the case D equals 4. Artinian Gorenstein algebras, codimension n, and so-called degree 4. What are the possible Jordan types? The Hilbert function is 1, n, something, n, 1. SLP is controlled here by has 1 of f. And double P is controlled here in the middle by has 1, 2 of f. As a matter of fact, it would be 1, 2 dual, but the dual of 2 is 2. Let me call this rank R. Sorry. R is the rank of has of f. and S, the rank of Hess mixed 1, 2 of F. So the result is that the Jordan type has this beautiful formula, and you can use the theorem, but I prefer to use the algorithm. I'm going to suppose unimodal n A. If the first Hessian has rank R, we got here the big string has length 5, here R minus 1, 5, 1, R minus 1 of length 3. And these guys if the rank of the mixed Hessian is S, it's saying that this is S. But maybe here we got something more. So here we have we must have a symmetric. So 5, 1, 3, R minus 1. S in this way. S minus R here. S minus R. And by symmetry, we also have S minus R here, 2 times S minus R. There is a misprint. He's S minus R. And then here, ones. How many ones? N minus S. Ones. 5, 1 plus 3R minus 1 plus 2. 2 times S minus R plus 1. 2 times N minus S by symmetry plus these guys here, A minus S. Let me produce explicit examples. And there is something wrong in the slide. This is the string diagram I just explained. In the case of double P, this double LP means that this is full rank n. I'm assuming that A is at most n. So just to plug this information. In this case, we only have strings of length 1 in the middle, because the rank from A1 to A2 of the multiplication map is full, taking a generic L. So we got this diagram. This is an explicit example. With delta 2, the delta, again, is the codimension of Z, which is the corank of the Hessian. And it means that there is two algebraic relations among the derivatives. And this is a formula of such type. And this is the string diagram. Let me explain this explicit string diagram. Sorry. One, 8, 10, 8, 1. 1, 8, 8, 9, 10. 1, 2, 3, 5, 6, 7, 8. 1. This, sorry. This is the longest diagram. The Hessian has corank 2. So up to here, we got this. Now we have to see that if the rank of the mixed Hessian 1, 2 is full or not, we have to compute the rank of Hess 1, 2. let me explain how to compute this rank. X1 u squared v plus x2 u v squared. That's the question. It's easy to see that A has the double LP by we have to compute this rank. That's the point. How it's easy to see that A has the double LP? We have to compute this rank. The Hess 1, 2 of F 1 x1, x2, x3, x4, x5. U, V, W. Block decomposition. X, U, x1, U, x1v. The derivative of f with respect to x1u is uv. x1v, u2. Now x2, u. v2, x3, u is u2, which is the same. x4u, x4w. Okay, that's it. 0 here, something. U squared, uv, v squared, u double, v squared, v double, no, u double, uv, u squared, v squared, v squared, v double, no, w squared. You have to compute this rank. You have, and this one. And I did it by computer. And I said that it is easy. It is easy to see, not so easy, but it's true that A has double P. Here is the dimension of A2, which is 10, as I said, 10. So if it has the double LP, we have this diagram. Let me put in this way. It's not so symmetric, but if we change it this way, it becomes more symmetric. So the Jordan type is 1, 2, 3, 4, 5. Jordan type of A 5, 1 plus 1, 2, 3, 1, 2, 3, 4, 5, 3, 5 plus 2, 4. This is the picture of the string diagram. and we have the same kind of result. By Gordon-Noether theorem, if n is less than or equal 4, then A has the SLP. Therefore, the Jordan type is the dual of the Hilb, so delta is 0. If n is equal 5, there is 2 possibilities, and delta can be as big as you want. In the special case, so-called degree 5. I do not have time to explain everything in so-called degree 5. Let me try to. This is the diagram in so-called degree 5, but I'm much more interested in discuss an open problem in so-called degree 5. A very simple open problem, just to finish the course with this very particular problem. A concrete open problem for variables and so-called degree 5. Again, by Gordon-Noether, in this case, the first Hessian is non-vanishing. So the only possible vanishing Hessian is the second Hessian. The Hilbert function is 1 and something, and 1, and I will assume this. A has SLP if and only if A has double P, because this Hessian is non-vanishing, so this second Hessian controls everything. If and only if has to have not 0. Sorry, we are in codimension 4, 4, 4. For the maximum possible Hilbert function A is 3 number of variables minus 1, 3, 2 in degree 2, 2 is 2, which is 10. For A, equals 4, it's easy to see that A has the SRP. From 5 to no, 5 or 6, we don't know. There is example of A failing SRP, or equivalently double P. We don't know. So we don't know the possible Jordan types in this case. For A 7, 8, 9, 10, we have the variations of Ikeda. Let me just make the string diagrams for this variation of Ikeda, this original Ikeda. Simplified Ikeda is X. Original Ikeda is the delta 2 in both examples is 1. Delta 2 is the core rank of the second Hessian. So one, two, three, 4, 6. Oops. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3. 1, 2, 3, 4. This is the longest string. The first Hessian is non-vanishing, and the second Hessian has core rank 1. So the string diagram, the Jordan type of the simplified Ikeda is 1, 2, 3, 4, 5, 6. 6, 1 plus 1, 2, 3, 4, 4, 1, 2, 3 plus 2, 2 plus 1, 2. Delta 1. This case is similar. The Jordan type of A is 6, 1 plus 4. Here we have 3 more because the Hilbert function here is 7. 1, 4, 7, 7, 4, 1, and here is 10. 1, 4, 10, 10, 4, 1. So we have 3 more here. 6, 2. Sorry. No. 3 is the same here, but here we have 3 more. 2, 5 plus 1, 2. Again, delta 2 is 1. So here we don't know. Here, delta 2 is 0. Here, we know algebras with delta 2, 0, and 1. And that's the question. What are the possible Jordan types for Artinian Gorenstein algebras? in 4 variables and cycle degree 5. You see? We don't know examples failing double LP for a 5 or 6, and we don't know, at the best of my knowledge, and we don't know if delta 2 can be greater than 1 if A belongs to 7, 8, 9, 10. This is the possible Jordan types in so-called degree 5 with double P. This is the string diagram. In the case having double P. The main reference for this last lecture is this paper, the Jordan type of graded Artinian Gorenstein algebras. And also we use some other results about forms with vanishing Hessian. And it concludes the course. I would like to thank ICTP and CIMPA by the opportunity. And that's it.